So I'd first like to thank the organizers for providing me this opportunity to present my work here. This work has been done in collaboration with Ashutosh Kumar, who is my student at BIT Mishra, with Dr. Trilchan Bagati at Tata Steel and Dr. Shubhashish Banerjee from IIT Jodhpur. This is a brief overview. I will start with an introduction to microscopic quantum heat engines and squeeze baths and describe our model. I will go to calculations of efficiency and power, and then finally to 2-qubit quantum engines, and the main focus will be on comparison between 1 and 2-qubit engines, and I will summarize. Now, this microscopic heat engines in both classical and quantum regimes have been a subject of a lot of interest in the last 2 decades or so. At this level, thermal fluctuations become important, which make these dynamics very different from the dynamics of macroscopic heat engines. And here is a model of a classical heat engine, which is frequently used. For example, this one here was used by Beschinger's group in 2012, where this is the macroscopic model, and there is an optical tweezer which mimics the effect of this piston over here, and there is a colloidal particle trapped in this optical tweezer that acts as the working system. And here is the quantum counterpart. I'll be dealing with quantum auto engine, where there are this is the simplest case, the two-state system. And here are the 4 strokes of the engine. The first stroke consists of these 2 levels getting expanded from E1 to E2, and these levels are denoted by omega C and omega H in our over here. And in the second step, this is an adiabatic step, which means it's not in contact with the bath. The evolution is unitary. In the second step, it's in contact with a hotter bath, and this energy gap remains fixed, so that this is like an isochoric process here, but the evolution is non-unitary. Then again, a unitary evolution, the bath is disconnected, and the energy gap decreases from E2 to E1, and finally, to complete the cycle, it's in contact with the colder bath, and the energy gap remains constant here. Okay, and the work is done during these unitary steps because there is a change in the energy levels, whereas there is no exchange with the surrounding environment. And heat is exchanged during these isochoric states because the energy gap remains same, whereas there is some energy exchange with the environment. Now, once we can get the density operators at these 4 vertices of the cycle, we can calculate all our thermodynamic parameters. Like the work can be calculated by difference in the expectation values of the Hamiltonian at between the extremal states of the unitary evolutions. The power is simply the work divided by the cycle time. Heat is calculated by the energy differences for the non-unitary steps. And this is the efficiency defined in the usual manner. It can be shown that for this engine, the efficiency is simply given by 1 minus omega C by omega H. So the omega C by omega H is the ratio of the energy gaps, the larger energy gap and the smaller energy gap and the larger energy gap. Now, here we introduce the squeezed bars. The squeezing is a process in which suppose you consider the Heisenberg uncertainty principle, and you have the normalized delta x and normalized delta p, which give rise to half, and each delta x and delta p contribute equally to that. But then if I squeeze the system, then I can stretch one of the uncertainties and reduce the other uncertainty, and yet keep the system at the minimum. The product of the uncertainties is minimum. These are the operators, these are called squeeze operators defined in that way, where z is some complex number, and these r and phi are called the squeeze parameters. Now, throughout this work, we found that phi is inconsequential, so phi doesn't affect any of our thermodynamic observables. So when I talk about squeeze parameters, it will exclusively mean r. And you see this effect makes the bath non-thermal because rho b, if rho b is the density operator for the thermal bath, applying the squeeze operator makes it a different density, the density operator, so that makes the bath non-thermal. And yet we know that the effective inverse temperature can be determined in terms of the actual inverse temperature of the thermal bath in absence of squeezing. Beta naught is the temperature of the thermal bath, and we can get this result which has been derived in this. And these are the evolutions for which we have used the Lindblad equations. I will not get into the details of this. And similar equations can be obtained for the 2-qubit system. 1 qubit and 2 qubit, both of which we have the Lindblad equation. And these master equations can be solved using this dressed state basis in which our Hamiltonian is diagonal. These are the 4 basis states. And this is our density matrix. So the entire task boils down to the solution of the master equation boils down to solving for the differential equations for each of the entries of this density matrix. And we see that not all of them are independent, because some of them are complex conjugates of the other. So essentially we solve for the 9 differential equations, independent differential equations, and we can get all the thermodynamic observables that we want. Here we have plotted a function of the power as a function of the ratio of temperatures of the 2 baths, both for 1 qubit on the left and 2 qubit on the right. And we find that the general observation is that for the 2 qubit system, the power is higher, the extracted power is higher. Now it operates on engine mode above this 0 line, because there the extracted power is positive. Below this, this is not acting in the engine mode. So we see that this is high, and there is a general decay with increase in Tc by Th, which is expected because the thermal drive decreases, Tc comes closer to Th. So there is a decrease in power output when we go to higher values of Tc by Th. We do the same thing as a function of the ratio of the energy gaps. Again, this is higher. This omega 0 is, now we are using 2 qubits, so omega 1 plus omega 2 by 2, the mean of the 2 frequencies gives our omega naught. Okay, so again the TQV or the 2 qubit engine yields more power. Now from this graph we can, at these peak values, we can calculate the efficiencies. This is the power at the peak values. The efficiencies can be computed by simply using the formula 1 minus omega c by omega h, and we will get the efficiency at maximum power, which we can plot as a function of Tc by Th using this family of lines. Okay, and here we have done this for the 1 and 2 qubit case, and we see that when there is no squeezing, namely both RH and RC are 0, we get the curves that are close to the expected Curzon-Elborn form, namely 1 minus root over Tc by Th, whereas if there is a finite squeezing, the curves deviate from that.
You have 2 plus 2 minutes.
Okay. Okay, but here actually we don't have a clear understanding why this 2 qubit system agrees so well with the Curzon-Elborn form, but this 1 qubit is slightly off from the from this form. We can plot the effective temperatures also, because there are 2 levels. We take the ratio of the populations of these 2 levels, and then we can equate that to a Boltzmann factor. Okay, then we can get this beta effective, and here on the left hand side we have plotted this beta effective as a function of RH. So the system is in contact with the hotter temperature bath, and we see these red points are the data points, and the black line is this expected form that was given in Manzano's paper. And we see we have done this for time of evolution both 0.2 and 2, and we find that it always agrees very well with the expected line, whereas in the 2 qubit system, for short time of contact with the bath, there is a deviation. The dotted line is the expected line, whereas these red dots are the one that we get out of our numerical solutions. And we'll come to that, why there is a deviation over here. And however, if we allow it to be in contact with the hotter bath for a longer time, again there is a perfect agreement between the theoretically expected inverse temperature and the obtained inverse temperature. Again, finally, we can also test the effect of the proximity of the spins. If the spins are very close, this R12 is the normalized distance between the 2 spins. If they are very close, we call that collective decoherence regime. If they are very far apart, we call that the individual decoherence regime, which is R12 equals to 10. And we see that in the individual regime, we extract more power in both 1 qubit and 2 qubit case. And the reason is here, it can be shown that if the spins are very close together from the master equation, it can be shown that there are two decay channels. If you remember, there were 4 basis states, E, A, S, and G, and there are 2 channels through which the system can decay to the ground state, E to A to G and E to S to G, and this E to A to G drops out if the spins are very close. So the decay rate is reduced, and so it takes a larger time to come to equilibrium. So this purple line is close to equilibrium, and so if it's like a quasi-static process, and we would expect more power from out of that process. And this is the reason why we got an out of equilibrium beta effective in the case of the 2 qubit system, because there also R12 was less than 1. So I will stop here. These are the summary and summary. We have studied 1 and 2 qubit system using Lindblad equations, and the general observation was TQE or 2 qubit engine has higher power than 1 qubit. And TQE showed a better agreement with Kurzon-L1 efficiency. TQE takes a longer time to reach stationary state because of the decrease of one channel. And
Okay, so let's thank the speaker.